Finite element method gives us the flexibility of using unstructured grid, but it is also a pain to work with unstructured grid because we have to do intensive bookkeeping in terms of managing the number of nodes, number of elements, what they are connected to and how they are connected to, so on and so forth. So when I am working on finite element method, without telling you how this entire gamut of manipulating and using the unstructured grid in the numerical methods that we are going to use is a very important step, and I don't want to leave without saying a word or two about how we are managing the unstructured grid itself. So we will start looking into the unstructured grid, the important parameters that we will be using, like the list of nodes, the list of edges, the connectivity matrix, so on and so forth, and also I am going to use simple MATLAB based program to generate an unstructured grid for a triangular domain. So remember, my domain itself is a triangle and I am triangulating it. So I am using unstructured grid to triangulate the triangular domain. Why did I take a triangular domain? Because if I take a circular domain or if I take a square domain, it is easy to use rectangular grid. I can make the rectangular grid so small so as to conformally map the domain. Whereas when I have a triangular domain, I am going to have sharp corners and I have to inevitably go and use triangles, and that is the power of finite element method. So I am going to use that example to study a problem for modeling using finite element method. Before that, it is important to spend some time on unstructured grid, what are they made of and how are they computed, how are they used in the finite element method. That is what we are going to see. So let us start with the problem we are going to look into, but before that, so let us look into the domain itself. So we start with the big triangular domain, and triangular domain has various points. So this is the first point, this is the second node, and this is the third node, and the fourth node is somewhere here, and the fifth node is somewhere here, and the sixth node is somewhere here, the seventh node is somewhere here. So these are the 7 nodes, and the lines are, edges are connected in this manner. So let me number them before I forget. So this is the fourth node, so this is the fifth node, this is the sixth node, this is the seventh node. So 4 and 5 are connected with a line, 5 and 6 are connected with a line, 1 and 5 are connected with a line, and 5 and 3 are connected with a line, and 5 and 7 are connected with a line, 6 and 7 are connected with a line, 6 and 2 are connected with a line, and 7 and 2 are connected with a line, and 4 and 7 are connected with a line, and 3 and 7 are connected with a line. As you can see, there are so many triangles. So let us number them one by one. So this is my first element, this is my second element, this is my third element, this is my fourth element, this is my fifth element, this is my sixth element, this is my seventh element, this is my eighth element, and this is my ninth element. So I am taking this problem from a very classical textbook. It's an introduction to numerical electrostatics by Lawrence Dvorsky. So the source of this problem is Dvorsky, and introduction to numerical electrostatics. Using MATLAB. So I encourage you to try also other problems from this book, but so as you see, this domain has various complexities that we are going to talk about. Even the simple domain of this sort, which is a triangular domain, which has been discretized by triangles, using triangles, and we have totally 9 elements so 9 triangles, and we have 7 nodes, and we have so many edges, and we are going to talk about all these aspects step by step. So first one what we are going to talk about is the number of nodes itself. So the first one we are going to talk about in this problem is the list of nodes. So let's write them down. So this is the second one will be the list of elements. So the list of triangles, this is the elements. And the third one we are going to talk about is the boundary conditions. So once we have that, we are going to assign them certain numbers, and we are going to use the MATLAB structure of manipulating the matrices to take the problem. So let's say for the list of nodes what we will have is node number, and we will have the x and y coordinate. So in our case we will be having 7 nodes, so it will go from 1, 2 until 7, and we will have various coordinates, x and y coordinates. So this will be the first one. Second one will be the list of elements. What we have is element number, and the nodes. So we will have 1, 2 and 3 nodes per element. So we have 1, 2 until 9 elements, and we will have the nodes. For example, in this case when we have triangle number 1, we have 1, 2, 6. So if you see this particular triangle, element 1, the first one will be 1, second one will be 2, and third one will be 6. We are going in the anti-clockwise direction, and we will stick to that throughout the example. So we will have 1, 2 and 6. Similarly for the second one, it will be given by 6, 2 and 7. 6, 2 and 7. You can go and look at it here. For the second one, 6, 2 and 7, so on and so forth. And the last one will be 7, 2 and 3. So 7, 2 and 3. So you can write the last one as 7, 2 and 3. So this is the way we are going to use MATLAB structure to register the list of nodes and the list of triangles. And the last point in the 3 aspects what we had is the list of boundary conditions. So let's also write it down. So the list of boundary conditions are going to be given by, so boundary conditions. So you have boundary nodes and then the node number and then boundary condition. So we have totally 7 nodes, so we will give them the value. So 1, 2, 3, 4, 5, 6, 7. These are the nodes what we have here. So for the problem what we are going to do, we will assign the value of the potential on these 2 particular nodes to be 1 and 1, whereas other nodes we will keep them as zeros. So we will put, except for 5 and 6, we will put 1, 1, whereas the other ones we will put as zeros. So this is the way we have going to start doing any problem. We have the list of nodes, we have the list of elements and the list of boundary conditions, and we have assigned them using a matrix, and we are also assigning the boundary conditions. Once we do that, we are able to start with the problem itself. But before that, look at the geometry one more time. So look at the geometry of the problem what we are considering. There are several elements that are there, and these elements have different lengths for edges and different areas, and they are going to impact the solution in different ways. Not all triangles have the same dimensions, so we have to somehow understand the properties of those triangles. One of the property or the geometrical property that we will be using is the area of the triangle itself. So if you have a triangle, let us say given by certain 3 coordinates, so we will take a triangle. So you have x1, y1, and then you have x2, y2, and you have x3, y3. The way to compute the area of the triangle is going to be simply given by A of the element is equal to x2 minus x1 multiplied by y3 minus y1 minus half x2 minus x1 y2 minus y1 plus x2 minus x3 y3 minus y2 plus x3 minus x1 multiplied by y3 minus y1. This is a very complicated big formula, but we can actually simplify it by using the matrix manipulation, and when you do that, what you will see is the area is given by half the value of the determinant. The determinant value is x1, y1, 1, x2, y2, 1, x3, y3. So once you do the determinant and take half of it, this will be the value of the area of the triangle. Similarly, for the basis functions. For the basis functions, we are assigning, let us say, linear elements, and we call them as, so let us say the potential inside the element x comma y is going to be given by phi1 multiplied by f1 plus phi2 multiplied by f2 plus phi3 multiplied by f3, where f1 is a function of x comma y, it is equal to a1 plus b1 x plus c1 y, and f2 of x comma y will be given by a2 plus b2 x plus c2 y, and f3 of x comma y will be given by a3 plus b3 x plus c3 y. So this is the way you compute the values of the basis function, and like before, what you can do is you will get a matrix equation of the form equal to something. So this would be matrix equation for each of the basis function. You will get 3 equations. What you will see is the right hand side of this equation, when you rearrange the terms, what you will get is for each of the elements. So you have, so what you will have is a1, b1 and c1. Similarly, you will have a2, b2 and c2, and a3, b3 and c3. So these are the elements that you need to compute the value, but you know the value for the geometry of them through 1 x1 y1, 1 x2 y2 and 1 x3 y3. Similarly, you can do that for the other ones, and you can see that there is a pattern here. So 1 0 0, 0 1 0 and 0 0 1. What it means is the first basis function for a triangle like this, and if say this is the first node, second node and third node, the first basis function will have maximum value here and minimum value at these 2 points. So these are like slopes, what you can see. If I can draw it in 3 dimensions, then you might be able to appreciate it. I will try my best to do that. So what you will see is so assuming that this is the so I am drawing the basis function in green stripes. So let us say this is node 1 and this is basis function f1. The f1 will have maximum value. So if this is 2 dimensions, so this is the x direction and this is the y direction. What you see is the value of the f1 is like a slope like this. So you have a triangle and you have another triangle with the base on the same point, and the maximum value, it's going on the 3rd dimension, which is the z dimension, and it has maximum value as 1 at the point at the node which is 1, 2 for, whereas it has value 0 at the node 2 and 3, whereas the basis function f2 will have the value maximum here and goes to 0 here. If you are trying to replicate that in this graph, let me try it. It will be having a maximum value here, will go to 0 at the other 2 points. So this is the value 1, so this is the value, this will be 1, so this will be 1. I hope you are able to see the 3-dimensional replication, and so the basis functions are going to have different values, and that is what you are going to see. For this particular case, the maximum value is at 1, node 1, the maximum value is at node 2, the maximum value is at node 3, the rest of the values are 0. So once you get this thing clear, first what you will do is, first we will compute the electric field, and from there we will compute the energy, and once you have the energy, we can use it to compute the capacitance. So we will start with the energy itself. So the electric field components, let us say, has 2 components, which are Ex and Ey. So we know that the gradient of the potential minus of the gradient of the potential, remember I am using partial derivative here because there are 2 variables in the space, x and y. So I have to use partial derivative, is going to be given by, so I know the value of phi from my earlier assumption. So phi is going to be given by phi 1 f1 plus phi 2 f2 plus phi 3 f3. Using this, in this equation, I am able to compute the value of Ex as minus phi 1 dou f1 divided by dou x plus phi 2 dou f2 by dou x plus phi 3 dou f3 by dou x, and knowing the value of dou f1, f2 and f3, I can write them in a simplified form as this is equal to, so let me strike this one down and I will write this one later, equal to minus phi 1 b1 plus phi 2 b2 plus phi 3 b3. So I can do the same thing for Ey, so I will write Ey here, equal to minus dou phi by dou y, this is equal to phi 1 C1 plus phi 2 C2 plus phi 3 C3. So this is the value for the electric field, so there will be a minus sign outside. So once I know Ex and Ey, I can compute the value of total electric field as E square is equal to Ex square plus Ey square, and that is going to be given by phi 1 B1 plus phi 2 B2 plus phi 3 B3 whole square plus phi 1 C1 plus phi 2 C2 plus phi 3 C3 whole square. Since the energy what we are interested in is not a function of x or y, we can directly compute the energy using the formula W equal to 1 by 2 epsilon E square. Remember this, we have computed this in the previous case, it will be a double integral, so that is equal to 1 by 2 epsilon double integral x and y E square dx dy. So we can substitute this value into this equation to get the value for energy, and what we will get is essentially E square multiplied by the delta of the triangle that we are going to model. So this is the area, delta is the area here, area of the triangle. So what you see is I am taking out the E out of the equation, and I have this value that is given by the area itself. And now what we are going to do is, now we are going to differentiate the value of the total electric field that we have computed with respect to each of the potential terms, and they have to go to 0. So the terms that must be added to the coefficient is what we are interested in, and we are going to do it step by step accordingly. So what I have shown here is how the various basis functions are going to impact on the computation of the electric field, how we can see the impact of the geometry of the triangle impacting on the total energy that we are computing, so on and so forth. So let us look at the geometry one more time. So this is the geometry that we are going to simulate for this problem, and we said we are going to assign for 5 and 6 a potential of 1. So let us go back here. So the source of the program what we are simulating is from this book. So let us go back to the starting of the program and see step by step what you are doing. So the program asks for an input file. So the input file is basically the file which contains the value for various parameters that we have discussed here. So these are the parameters. So let us look into the parameter one more time. So these are the parameters. So these are the input files, inputs that we are going to give using the input files. So the file name we have to give a generic name, so we will call it as input, and then various parameters will get loaded. So the node data will be loaded into the node file name, and then the triangle data will be stored in the triangle name. So these are the elements, and the boundary conditions will come from the boundary conditions file. So once we get that, we are going to load those values into each of the parameters, and we are going to compute the number of nodes using the length function, the number of triangles using also the length function of these individual parameters. And once we do that, we are able to assign certain parameters for pre-allocating the variables that we are going to use into the code. So A, F and B. A is declared as sparse matrix. The reason for doing that is it actually quickens the code. If you are interested in writing codes that are running fast, you have to use certain inbuilt functionalities of MATLAB that will allow you to declare certain matrices as sparse so that the calculation can be done quicker. So once we do that, we are able to go through all the triangles and collect the data that we are interested in. For example, the area information that I have described, so it's half of the determinant which we are calculating, and these are the parameters that we have described in the coefficients A1, A2 and A3, B1, B2 and B3 and C1, C2 and C3. Once we have that, we are able to calculate the value of the potential at various points in the triangular domain using a simple MATLAB calculation where phi is given by inverse of A multiplied by F and where F is the boundary conditions. As you can see, I am setting the value of the boundary to be 1 for certain nodes, whereas I am setting the boundary to be 0 for other nodes. So 5 and 6 will be in this example set to 1, whereas the other ones will be set to 0. And once we have that, we are able to generate the mesh, and we are able to also calculate the capacitance as a function of various points that we are interested. So it will be a function of various points. So let's run this code. Once I run this code, it is going to ask me for certain inputs. I said the input name will be input, and what it does is it's initially calculating various things. In our case, the total number of nodes what we have is going to be 7, and the total number of triangles what we are going to have is going to be 9, and the total number of boundary conditions that we are going to assign is going to be 5. So why 5? Although there are only 3 here, if you look at the case here, there are only 1, 2 and 3. We are going to also force certain boundary conditions for these 2 nodes. So that's why it's going to be 3 plus 2. And once we do that, we get the value of the capacitance. So let's look at the field plot itself. So this is the potential plot. What you are seeing is the 5 and 6 nodes are given 1, whereas the other nodes are given 0, and the field plot looks like this for this problem. And the capacitance that we are going to compute for this problem is given by the value that we have printed in the MATLAB file. So what we are getting is 105.83 picofarad. So this is an excellent program for you to learn 2 things. One thing is how unstructured grids are used in finite element method. So we have talked about the advantage of using an unstructured grid, advantage of going to finite element method, but we have not really covered the nitty-gritties of manipulating unstructured grid, managing the data and using those data in computation. So what I have tried to show is a very basic aspect of the unstructured grid. So you get to know what are the important parameters in the mesh that we are generating, the list of nodes, the list of elements, the connectivity of those elements, the boundary conditions, so on and so forth. I have also showcased some simple calculations that you have to do to calculate the parameters like area, the basis function, so on and so forth. And once we have that, you are able to assign boundary conditions to the problem, and you are able to simulate and see how the finite element method works for that problem. So we encourage you to practice this code at your free time and get a sense of how the finite element method works. Thank you.